Hi guys, this is the second video for chapter 1. Just remember there's going to be 3. So last time we talked about matter and just generic atoms. Now we're going to talk about the subatomic particles like protons, neutrons, and electrons. And then we're also going to talk about isotopes. Also for this section, make sure you have a calculator. If you don't, you're going to need one. So just remember from chapter E or 0 that qualifiable, those are observable data, so like color, shape, smell, things like that. Quantifiable is measurable. So just keep in mind that that's going to be a number. Remember, all numbers have units, and measurable things are also going to take into account of sig figs. So first, we're going to go through atomic theory and the history of atomic theory. I'll let you know the people you need to know, but Democritus is one of those. And he was a student of Lysippus, but really Democritus is the one that got credit. And he was the first to propose that matter was composed of small, indestructible particles that he called atomos at the time. And that's where the word atoms come from. All right. Also at the time, just remember that Plato and Aristotle were pretty popular. I'm sure you've heard those names before now, but maybe not Democritus. They thought everything was in ether, and everybody believed Plato and Aristotle for about 2,000 years. So while Democritus was right, we kind of just ignored his theory because it seemed weird and nobody knew him. But after that, it was about the 1700s when people decided, oh, Democritus was actually right. Before that, we just thought there were the elements and there was this ether. So then in the 1700s, it was the late 1700s, Dalton came up with his atomic theory, and you will need to know all the parts of his atomic theory, but he kind of put together other ideas, and then he had some of his own, but he put them all into one fluid theory. So here's his theory. Again, you can, of course, print this if you want or have it up while you're taking the test or the quiz. That's absolutely fine. But he said that each element is composed of those tiny indestructible particles, which are atoms. He said that atoms of a given element have the same mass and other properties that distinguish them from the atoms of other elements. Okay, that one's actually not true, and we'll talk about that one in a minute. So we know this one now. Number 2 is not true. Atoms also combine into simple whole number ratios to make compounds, which is accurate. And then atoms of one element can't change into atoms of another element. And in a chemical reaction, atoms change only the way they're bound together with other atoms, which is accurate, unless we're doing nuclear chemistry, which is a whole different scenario. The law of conservation of mass is super important. This will come up multiple times, and so will the law of conservation of energy, which we talked about in chapter 0. So just remember, this is that matter cannot be created or destroyed. So whatever we start with is whatever we're going to end with. And here in this image, they're showing you with mass, and there are some questions on this. So just know on the reactant side, it must equal the mass of the products. So if you have to add them, you add them, and they have to equal the other side. It's really not that hard. It's kind of like algebra where the arrow is the equal sign. So there was also the law of definite proportions. You just need to know what the law is. I'm not going to ask you any math questions on it. And it just says that all samples of a given compound, regardless of how you prepared it or where you got it from, that they have the same proportions. So this is just saying water is always going to be 2 hydrogens and 1 oxygen. If it's something else, it's no longer water. So that's all that law is saying. The next law is the law of multiple proportions. And this says that when you have 2 elements, they can form different compounds as long as their ratios are different. So this is kind of like carbon monoxide and carbon dioxide. So carbon monoxide has 1 carbon, 1 oxygen. Carbon dioxide has 1 carbon and 2 oxygens, and they have super different properties. So carbon monoxide, as most of you probably know, is the deadly gas that comes mostly from exhaust pipes in cars, even like gas stoves and heaters, which is why if you have a gas stove or heater in your house, you should have carbon monoxide detectors. We do in our house. Our house is gas. But carbon dioxide is something you breathe out all the time, and it's not harmful to you when you breathe it out. The next person, and you will need to know this person, is J.J. Thomson. And what J.J. Thomson did is he used the cathode ray, which you also need to know that. And with the cathode ray, he was able to discover electrons. Okay, so all of this up here is what you need to know for him. You also need to know that the electrons were the first subatomic particle to be discovered. And it had to do with charge. Okay, so what happened in the cathode ray was he shot cathodes through this machine, and some of them were attracted to the positive side and others were deflected from the negative side. And because that, we knew that opposites attract and that the same charge repels, and so he knew there must be something negative in the atom. All right, because of that, opposites attract. He also came up with the plum pudding model, which you're going to need to know. Plum pudding was something popular back then, but now this is kind of more like a chocolate chip cookie or a blueberry muffin. Really, it's where the electrons are just kind of scattered throughout the sphere of positiveness. So if we were going with the chocolate chip cookie, the chocolate chips would be the electrons and the batter would be the positive charge. But we knew there was a positive charge. We don't know that they're protons yet. The next person is Rutherford, which you will need to know him. You also need to know the gold foil experiment. Okay, so Rutherford shot alpha particles at gold foil, and they should have all gone through if the plum pudding model was correct. However, the plum pudding model was not correct. It hit some very small, dense piece. Sorry, y'all, my dog is stretching. And so when it hit that dense piece in the atom, it deflected off some also bounced back. So he is responsible for the nucleus, which is that small dense piece in the center. He's also responsible because of that for the proton. So Rutherford used the gold foil experiment to discover the nucleus, that small dense center, but also the proton. Because of that, he's also responsible for the nuclear theory because he discovered the nucleus. And something to keep in mind is that most of the atom is empty space. It is so much empty space that if you were to put a marble on the 50-yard line in Cowboy Stadium, that would be the nucleus, like a normal sized marble, and the rest of the stadium, the entire stadium, not just the field, would be the atom, and it's just empty space. So the amount of space in an atom that's empty is very, very large. And then again, because we knew that there was a positive something in the atom, the protons are also accredited to him. Chadwick is the last person. This was much later, 1932, and that's when we discovered the neutron. And that's because we had this missing mass, and we knew it didn't have a charge, so that's why they're called neutrons. This is kind of like dark matter or dark energy out in space. We know it's there. We don't know what it is. And we know how it's affecting things. We can see that. And it was the same with the neutrons, but we just don't know exactly what it is. So the mass of the neutron will be similar to that of a proton because we knew about the missing mass. Also, we know it has no charge because we weren't affecting charge anymore from the electrons and protons. So just so y'all know, all atoms have 3 subatomic particles, and those are the ones we're going to focus on: protons, neutrons, and electrons. You will need to know the basic mass and the basic relative charge. The other charge and mass, those are more used in physics. They occasionally come up for us, but not very often. I think some of it comes up in the POGL, and it's really not hard. You just use dimensional analysis. Okay, but really we say the mass is 1, 1, and 0, and then the charges are positive 1, 0, and negative 1. Electrons are just so small, we say they don't have mass. They do actually have mass. They're just really tiny. All right, so all elements have protons, neutrons, and electrons, or they have the ability to have those. And the protons are what define the element, and that's what the atomic number is the protons. Okay, that will be the top number or the whole number on your periodic table. So this is the atomic number, okay? And the periodic table is arranged by the atomic number or the number of protons. When we see isotopes, an isotope is the same type of element, which means it has the same number of protons, but they have different neutrons. And here in these isotope notations, this bottom number, that's the atomic number. Or protons. Okay, and you can always just pull that from the periodic table because protons don't change for a specific element. So again, atomic number is at the bottom. That top number is called mass number, and that is the protons plus the neutrons. So you can always find the number of neutrons if you have the mass number because the atomic number doesn't change. Okay, sometimes isotopes are also written this way, where we say the element name and then we put the mass number behind it because you need to know how many neutrons you're using. This is pretty common with carbon-14 or carbon dating. You may have heard of that. That's specifically carbon-14, which has 8 neutrons instead of 6, like is on the periodic table. And we use that because it decays over a long period of time. You'll talk about nuclear decay in chapter 14 if you take chemistry too, but that's how we date all organic material if it's old enough. Next thing we're going to do is talk about natural abundance, and all isotopes are found in some amount in nature, and the one that has the most abundance, that's what the mass on the periodic table is closest to. Also with ions. Ions specifically, you need to know what these are. Those are atoms that gain or lose electrons, and they'll become charged particles. A cation, and cat has plus in it from the T, so that's how you can remember those are the positively charged ions. These ones lose electrons. The anions anions are normally considered negative. They are negative. And remember, the prefix "an" normally means opposite, or you can think about ants. Ants are normally not a good thing, especially for me and my daughter. We're super allergic to them. So just remember, "an" is negative, and they will gain electrons. And I will always abbreviate electrons E-, just for ease instead of having to write out the full word electron. Okay, so here we're talking about the periodic table, how to determine its isotope symbol, what's its atomic number, what's its mass number. We're also going to go through and find how many protons, neutrons, and electrons they have. If they do not show a charge, you assume neutral. Okay, which means the protons are equal to the electrons. And to find charge, you're going to do protons minus the number of electrons. Okay, so here we want the atomic number, the mass number, and the symbol of chlorine with 18 neutrons. So chlorine is the symbol. And chlorine, if you look on the periodic table, it's number 17. It has 17 protons. And then here it says we have 18 neutrons. So this mass number, remember, is protons plus neutrons. And then I also want us to go ahead and identify the protons, neutrons, and electrons. So it has 17 protons, 18 neutrons, and because no charge is shown, it also has 17 electrons. Only when charges are shown does that change. For B, it's chromium, because that's what Cr is. And we've got 24 and 52. So protons-wise, we've got 24. No charge is shown, so electrons are also 24. And there's a table that's going to be on your one of your POGLs. It's the ions, isotopes, and atoms. And that one has a table where you'll be identifying all of this. The neutrons will be 24 minus, or 52 minus 24, which is 28. Yeah, 28. Okay, so please let me know if you need any help with this. There's some of this on the POGL. There'll be some of this on the homework, on the test as well. Oh, let me see. These bottom ones, we can go ahead and go through these examples as well. So we've got a carbon. I'm going to write this one up here. Carbon was 7, so carbon is 6, which means its mass number, if it has 7 neutrons, is 13. And then the electrons are also going to be 6. For this bottom one, protons and neutrons. And just note, if it ever says atom, it's talking about no charge. Okay, here we've got 19 protons, 20 neutrons, and 19 electrons, because we've got that no charge situation happening. The last thing for this video is going to be average atomic mass, which pulls in that abundance. This is kind of like calculating your grade, because your grade is based on different percentages, like homework has more weight or less weight than tests, and labs are going to have more weight than homework. So because of that, we're going to use an equation, and I don't love this one. This one's kind of confusing, but the atomic mass is equal to the sum, that's what the sigma means, of the fraction of the isotopes times the mass. I normally do, so mass times percent divided by 100, because you want it in decimal form, plus mass times percent divided by 100 again, plus, and you just keep going with however many they have. Okay. So here in our first example, we've got chlorine. Wants us to calculate chlorine's mass, so we've got a percentage times a mass, and another percentage times a mass. Now, sometimes they don't give you mass in AMU, and if they didn't, you would need to use this mass that's denoted after the element. So I'm going to do mass times percent. So I'm going to do 34.97 times 75.77 divided by 100 plus 36.97 times 24.23 divided by 100. And then this one, that one only has 2 isotopes, so that's all we're doing. In my calculator, I'm going to do 34.97 times 0.7577 plus, don't forget your parentheses, 36.97 times 0.2423. And I get the mass for chlorine is 35.4546. I'm going to keep whatever is after the decimal here in my original mass, and my unit is going to be AMU. Okay, so this is my answer. So there it is, 35.45 AMU. Also, if you look on the periodic table, that is the mass that's shown on the periodic table. So we're very close, which is good. Those are true numbers. The last thing, so this one's not a calculation, but this is a mass spectrometer. We do have one of these at Eastfield, although obviously we're not up there using it. And we don't use it in Chem 1, which is a lower level chemistry. This is much higher level chemistry that you would use this for. But it helps measure the mass of atoms and molecules. And what happens is you put your sample in, and it uses magnets and charge to break apart the different isotopes. So then you can see how much of each there is. So here in this little picture, this is what we use mass specs for, to see this picture at the bottom. And notice it says we've got the most of chlorine 35 and just a little bit of chlorine 37. So I'm going to delete all of this part out. So that means that most of it is chlorine 35. It's going to be a little higher than 35. And when you look at 35.45, so it makes sense that we canceled out some of that. And really this amount is 36. Okay, because those two average out to 36 when we cancel them out. So it does make sense. At that point, I've got about, I don't know, 20 or maybe 33%, 36 and 67%, 35 or so. So you just kind of estimate that way. All right. If you'll have any questions, please let me know. This is the end of this video. I'll see y'all next time. Have a great day.